slide called spot.
Something like that.
I don't believe that there's much explanation to do for now, but I will anyway. What do you do when you're not explaining? Theorem, define a function f by 1 over x equal to 0, or 0 when x equals 0. Then f is not continuous for the domain, for the domain closed interval 1, -1. That's not a correct domain.
You mean -1 to 1, right?
Yeah. I checked over, today I actually checked over things, I think. Yeah, quote-unquote exploration, though some of this information is kind of used later in the proof, so I wouldn't say it qualifies as exploration, just first steps. Simply by looking at this piecewise function, carefully looking, noticing that 0 when x equals 0, simply by looking at this piecewise function, we can see that we must show that f is discontinuous at 0, just by the way that function f is enticingly constructed, quote unquote. To do to somehow show that the limit of f of x as x equals 0 is not equal to f.
Wait, you mean f is 0 on the right side, right?
Ah, yes. Yeah. I don't. Blue, lovely. As well, by looking at Desmos, let's yank it up quick. I should be using my Mathematica, your Mathematica subscription.
Yeah.
This is play a part in visual. This isn't good at all. Just carefully look at that.
So I can actually see it. Are you sharing just that window? So I don't see the decimal stuff?
Oh, right. I forgot I was screen sharing just the window. Yeah, I just that it.
Oops.
Anyways, one can tell upon observing the graph of this function, sine of 1 over x, that it begins rapidly oscillating as x approaches 0. Since this function has a range... Why do I keep doing this? Has a range of -1, 1 for the domain -1, 1. You can simply set epsilon sufficiently small. After all, by the definition of limit, it only need be true that epsilon is greater than 0. Am I lagging?
No, I think you're good. So to make sure I'm following, you're saying we're going to make epsilon small enough that this thing oscillates outside of the epsilon bars from -epsilon to epsilon, because we know it keeps hitting -1 and 1. So the point to your last sentence.
Could you possibly say that again?
Sure, yeah. I was asking to make sure I'm following. In your last sentence, you're saying the strategy will be to take epsilon sufficiently small that this function wanders outside the epsilon bars, so to speak, -epsilon to epsilon near 0, because you know it keeps oscillating wildly up and down from -1 to 1. Is that the idea?
That is correct.
Good. Okay. I'm happy.
Wait, what? Oh my god. I just realized that Adobe is being nice today and skipping the blank spaces.
You can disable that if you want, by the way. I only put blank spaces so I have room to draw with Epic Pen.
Oh, that explains why my mind wasn't doing that. Wait, here? Yeah, it's because I borrowed your template.
Oh.
As I mentioned earlier, we can simply make our epsilon sufficiently small, and sufficiently small in this case is going to be epsilon equals 1/2. Suppose by way of contradiction that there exists a delta such that the absolute value of f of x minus our is true for the domain -delta to delta closed. That is implied in this limit. I'm quietly judging myself as I'm reading my own work. Good. We can the periodicity of the sine function and see that we can choose m and n sufficiently large such that First variable definition x1, x sub 1. What's the proper way to say that? x1?
I say x1, but I've heard people say x sub 1. Either fine.
Okay. So, we can define x sub 1 to be 1 divided by the 2 times 2 pi and an n sufficiently large plus pi over 2. Similarly, we can define a x2 equals 1 over 2 pi and yeah, I copy-pasted it. It didn't work. Good job, Self.
So you want m in the second one, right?
Let's say this is m.
Okay.
2 pi plus 3 pi over 2. This is going to work for us because we have it set up so that's 1 over x, sine of 1 over x, so this is going to simply invert it. And in turn, sine of this is going to be equal to sine of pi over 2. When m and n are integers. Yes, I need to make that clear, because I didn't see it in this slide. Why is that? Once again, we can make m and n sufficiently large. These two variables here are in the domain negative delta 2 delta. We can then see regardless of, I don't see, yes, that's why I said that. We can then, regardless of our choices m and n as long as integers, that f of x1 equals 1 and f of x2 equals negative 1, contradicting our attempt to limit. I'm thinking what I was trying to contradict here exactly.
Yeah, I'm going to hold your feet to the fire on this one. So you say this contradicts that f of x minus L is less than epsilon, where epsilon is a half. So explicitly, can you explain why it could never be true that absolute value of f of x minus L is less than epsilon holds on that domain, given what you just found? Or in other words, what is the contradiction?
As I try to go up a slide. So our contradiction here was we were attempting to show that there does not exist a delta such that this is true for an epsilon of 1/2.
Yeah. And then why? Okay, so you say that for any delta, you can pick these two numbers, so that within my minus delta delta interval, I hit 1 and minus 1. And you claim this contradicts that all of the outputs are within distance 1/2 of L within that interval. So why exactly does it contradict the assumption that all of the outputs are within 1/2 of L?
Because L is 0 and 1. I believe that I can simply say that 1 is greater than 1. Or is that assuming too much? Well, assuming that I know too much already.
So the first thing you said is that if L is 0, this works. That I agree with. Because if L is 0, then you would say, yeah, of course I can't get f within distance 1/2 of 0 if it's going to keep hitting 1 and minus 1, because 1 is greater than 1/2.
Oh, wait. I don't know why I said L equals 0, because...
Yeah, we're just proving a limit. Well, actually, for the way you stated the problem, which is just that it's discontinuous at 0, it's enough to let L equal 0. So let's just be slightly more general. Because actually we could show that this doesn't work for any L. So why is it true, based on this slide, that whatever L you pick, it's never going to work that f is within distance 1/2 of L if it keeps hitting 1 and minus 1?
Because if it, for example, if our L was 1, then there is no way our quote-unquote range could include our -1.
Yeah, good. That's the idea. So, I mean, formally you could do this with the triangle inequality, right? Because the distance between f of x and L, you can bound with the triangle inequality. I think you want the reverse triangle inequality to be the distance between, say, 1 and L Shit, I don't see exactly how to do it now. Yeah, I would have to write this out. But to do it formally, you could say you could never be within distance a half of some L if I keep hitting 1 and minus 1, because the distance between 1 and minus 1 is larger than a half.
Yes.
Okay. Yeah, okay, sorry for interrupting. I'm now happy that you understand this.
Thank you for interrupting. Regardless of our m and n, that f of x1 equals 1 and f of x equals negative 1. Which is, yes, I already said this, but contradicting going approaches 0, the limit does not exist, and therefore continuous for the domain negative 1, as f is discontinuous at 0. Are you lagging?
Nope.
Think.
I'm happy with this one.
Cool. Yes, this, once again, we are operating on the same function. We have to prove in these following slides our function f satisfies the conclusion of the intermediate. To show that this function f is consistent with the conclusion of the intermediate that I shall list here and say here, if f takes on two values somewhere negative 1, 1, then takes on every value in between, we must consider the potential placements of two values a and b. First, let the closed interval ab be a nominal subset of negative 1, 1. This is the turning the statement that a must be less than b and that it must be a subset of. It's basically my way of wording what you said. Anyways, yeah, I didn't need to explain that. First, we consider the case where 0 is not an element of the closed interval AB. It is automatically true that it's continuous for the closed interval AB, as f is only discontinuous at 0. I don't believe I proved that.
You can prove it in one line from what we said before, because you proved on consolidation argument 2 that sine is continuous, and you also proved that the composition of continuous functions is continuous. So sine 1 over x is continuous, except where 1 over x is discontinuous, which is only 0. So that I think that's fine to skip.
Okay. So it's close enough to justify it.
Yeah.
Alright, to continue. Therefore, by the intermediate. Did I skip a step? No, I didn't skip a step. I'm just forgetting what I wrote down. Continuing from where we left off before, as the second time. Therefore, by the intermediate value, we can choose a number y between f of a and f of b, such that there exists a number c in the open interval AB such that f of c equals y. I don't know why I said pretty generic for now. This is basic logic right now. Now it's not. In the case where 0 is an element of the closed interval AB, we must show that for y in between f of a and f of b, there exists a c in the open interval AB such that f of c equals y. We must show that this c exists. This is the important bit. We already have that. Saying it in English, f of a and f of b are in between negative 1 and 1 or equal to each of these. Negative 1 is less than or equal to. Saying that both in English and math. Then in turn, negative 1 is less than or equal to y, less than or equal to 1. We can convert sine function to do our bidding here, as we are operating within its domain, and apply. That doesn't look quite right.
Yeah, perfect. If you ever do a superscript that has more than one character, so not just like x squared, but x is like minus 2, you have to put curly braces around it, or it'll just use the first one.
Cool. forgetting things when you're in a rush. We apply the inverse of sine to y to get that there, such that sine of c prime equals y. Once again, we can exploit the periodicity, the sine function, and let c equal 1 over 2 pi n plus c prime, where n is sufficiently large enough that c is in the closed interval ab. We then have that f of c equals sine of 2 pi n plus c prime equals sine of c prime equals y. Therefore, f of c equals y, and the conclusion of the intermediate value theorem is satisfied for this function f.
This all looks good to me. So again, let's see. You don't need to prove this, but just can you say just a sentence just to check that you're clear on the argument? Why can we always pick n large enough so that c lies in that interval?
Yes, I forgot to mention that n is once again an integer in this case, since I can't exactly remember the definition of periodicity, but essentially we already have that f of x that we're working on is sine of 1 over x, and it gets basically double inverted, so we have sine of 2 pi n plus c prime, and 2 pi n, where n is an integer, is the period of sine. So every increase of 1 in n is going to be the same answer as the previous, or if it were to be 0.
Okay, so you're explaining why f of c is y using periodicity of sine, so that's good. But why can we always find an n? Maybe it's an integer, I don't really care, it could be a real number, but why can we always find an n large enough so that c is in the interval ab?
Oh, I went totally different way. Because we can just simply, since c is a fraction, we can increase the size of the denominator enough that it will be small enough that it is in AB, or large enough, whatever. We're assuming that in this case, our AB includes 0, so it's probably the case of small enough.
Good, okay. That's the key. Yeah, since AB includes 0, if you make that denominator huge, you're getting close to 0. So you know, since 0 is in the interval, you can get very close to that point in the interval. Good. Okay, I'm happy with this.
Is there any further questions on this slide?
None for me.
Now, these next 2 slides are gonna suck. Oh, wait, I'm missing a title on this slide. It's missing indentation. What's wrong?
Oh, the humanity.
Alright, so allow me to remember. I believe that we are proving the converse of the intermediate, correct? You're the student.
You're proving the converse with the one extra assumption that g takes on each value only once. That's the extra piece.
Ah, yes. Use a function satisfying the conclusion of the intermediate. Once again, I don't need to say that again. And takes on and it outputs each value only once. We shall show that g is continuous by way of contradiction. Suppose by way of contradiction that there exists a point A where the limit of g of x as x goes to a does not equal g of a. We can take the negation. Yes, we can take the negation of the definition of a limit at a continuous point to get what is meant by a limit not being continuous at a point. And I'm going to quote Christian's fine work here. End quote. There exists some epsilon greater than 0, for which it is true that no matter what delta you pick, there will always be some values of x where the absolute value of x minus a is less than delta, but still the absolute value of g of x minus g of a is greater than epsilon. We can then choose a value of epsilon such that the previous statement is true, and in turn it is true that regardless of how close we get to a, then our input x will either have that g of a plus epsilon is less than g of x, or g of x is less than g of a minus epsilon.
Can you explain the negation piece again?
There's silence, I'm scared.
Oh, sorry, maybe we're lagging. I was saying, could you explain why that is the negation of continuity at a point?
Unfortunately, I'm thinking about how to... I do not totally understand negation.
Okay, let's do the easy question. So, if I just take the English sentence, uh, I'll use the stupid example from before. Everyone loves someone. Every human loves at least one other human. What is the logical negation of that statement?
Oh wait, this is simply taking everything and basically putting it to an... So, no one loves everybody?
No, so that's not the negation. No one loves everyone is a different statement. So everyone loves someone. Let's just go through the steps, step by step. So the original statement is no one loves, or sorry, everyone loves someone, is what we started with. Then I put a not in front of that. So it is not true that everyone loves someone.
Lag spike.
Oh shit. Why is it always when I'm doing something the lag spike? Is it better yet?
Oh god, the lag.
Ah!
You begin by saying it is not true that.
Okay, yeah, so original statement, everyone loves someone. Then you not that. So we're taking a logical negation, so it is not true that everyone loves someone. Everyone loves at least one person. So if it is not true that everyone loves at least one other person, that means there exists at least one person who does not love anyone. Right? If you can find a single counterexample, if you can find one human who does not love everyone, then that is enough to falsify the claim that everyone loves someone. So the logical negation of the statement, everyone loves someone, is the statement, there exists at least one person who does not love everyone. That's the right negation. The negation is not, as I think we suggested before, that nobody loves everyone. Or what was I forget what you said that actually. Was it no one loves everyone, or I forget. I don't even remember what it was. Oh, you muted yourself.
My false statement was no one loves everybody.
No one loves everybody. Okay. Okay, so it's not the original statement is everyone loves someone, and you said nobody loves everybody. Okay, so right. So to do negation, I think you have to be a little more careful and ask yourself what would have to happen for the statement to be false. And in this case, it wasn't that nobody loves everyone. It was just that you need one counterexample, one person who doesn't love someone. Okay, why am I using this stupid example about people loving people? Because in this case, the definition says for every epsilon greater than 0, there's a delta with certain properties. That's just like saying for every human. Did it lag spike again?
But?
Oh, I just saw the quality drop, so I thought it lag spiked. Are we still okay?
Yeah.
Okay. So why am I doing this stupid example? The original statement is for every epsilon greater than 0, there's a delta with certain properties. That's like saying for every human, there's another human with certain properties. Namely that the first one, that's the second. To negate this statement, just as we negated the statement, everyone loves someone, by saying the negation is there's at least one person who doesn't love anyone. To negate the statement that for every epsilon greater than 0, there exists a delta with certain properties, what you say is there is at least one epsilon, that's like a one human that doesn't love anyone. There's at least one epsilon for which there's no delta that has those properties. That's the way to negate it.
Okay.
Very long-winded. Does it make more sense now, or is it so confusing? I can write more examples if it's confusing.
I believe I'm understanding it better.
Okay. Good. Sorry for the interruption. I think I'm happy with the rest of the stuff on this slide.
Thank you for interrupting. That's not me being sarcastic. Click. Alright, I believe that we have gone over this slide successfully. Okay, referring back to the case that we have. We can then choose a value of epsilon such that the previous statement, the one that we were just talking a lot about, is true. And in turn, it is true that regardless of how close we get to A, that our input x will fall into two categories. G of A is less, G of A plus epsilon is less than G of X, or G of X is less than G of A minus epsilon. We shall assume the former case is true and work with that. Without loss of generality, assume the former, and for a newly defined input x of 1, it is true. Therefore, G of x of 1 is greater than G of A plus epsilon. From this we then have that there exists a C in the interval, open interval, A x1, so that G of C equals G of A plus epsilon over 2. We can then once again refer to the fact that we have assumed G is discontinuous at some point A, and therefore there exists more values x such that G of X is greater than G of A plus epsilon. We can then say x sub 2 is another value on this interval, open interval AC. We have now found that A is less than x sub 2 is less than C is less than x sub 1. Let's see, is that correct? That is correct. And that G of x1 and G of x sub 2 are greater than epsilon. And that G of C equals G of A plus epsilon over 2. By the intermediate value theorem, we can see that this information contradicts our claim that G of X, G that outputs only English, that each number only once, as we see that there exists phi sub 1 in plus epsilon, and another value phi sub 2 is in C x1, where G of y2 equals G of A plus epsilon. These are two unique outputs that output the same. Yes, that is correctly worded. This contradiction then verifies our claim that G must be.
Okay, so third sentence. From this we then have that there's this.
1, 2, 3.
Why is that true? You say from this, but from what exactly?
Did you say that again?
So the third sentence, when you say from this, we then have that there exists a C in the interval, which G of C is G of A plus epsilon over 2. Why is that true? What is the this, the from this, that you use to show that that's true?
Yes, that is by the intermediate value.
Good. Okay. So you're assuming that we're satisfying the conclusion of the IVT, and that's what you use there.
Yes.
Okay. So fifth line from the bottom.
Fifth line from the bottom. 1, 2, 3, 4, 5. By the intermediate value theorem?
Yeah. The sentence that says by the intermediate value theorem. you start by saying by the intermediate value theorem, but then you say that this contradicts our claim that G outputs each number only once. So just to be a little more specific, what is the
Yes.
intermediate value theorem being used to get in that sentence?
In this sentence, we are using the intermediate value theorem to show the statements y I sub 1 is in x sub 2 c, and similarly y sub 2 is in the open interval c x1.
Good, okay. So yeah, in both of those you're saying the IVT says you hit everything between 2 points, and we have 1 point, G is C, which is G of A plus epsilon over 2. That's less than epsilon, and you have another point where G is greater than G of A plus epsilon, so you use it twice to get 2 points that hit that intermediate point. Okay, now I think I see it makes sense.
There was something along these lines in English class, where you refer to things before you do them, not like an entire sentence before you do them. Is there any further questions?
Yeah, I think that's good. So I guess, can you explain the punchline of this sentence? Not this sentence, this whole exercise. So why is this exercise interesting? What was the big picture of this part C of 11.1?
Sorry, could you say that again?
Yeah, so in your own words, what was the goal or punchline? Like, what was the big picture of this exercise, which is part C of 11.1? What were we trying to do in this problem?
It would seem that we were trying to show that even though a function, refer back to, that's spot. Wait, down the theorem bit for this. Lovely. So for a function g, we have shown that if something satisfies the conclusion of the intermediate value. That doesn't seem entirely right, though.
Wait, what doesn't seem right?
I believe that I said that if something satisfies the conclusion of the intermediate, that it is continuous.
Yeah, that part's not quite true. It's not true that everybody who satisfies the conclusion of the IVT is continuous, but there's a certain extra.
Oh, in this case where it's either strictly increasing or strictly decreasing.
Yeah, or just more generally, any function that hits the same, or only outputs each value once. I agree, strictly increasing and strictly decreasing both have that property. They might even be the only one. Yeah, okay, you're totally right. Good, I didn't realize that was the same thing. Yeah, so you could have said, in the intermediate value theorem, we proved if continuous, then you hit every point between two endpoints. You could ask, is the reverse true? If you hit every point between two endpoints, must you be continuous? The answer in general is no. But if you say, if you hit everything between two endpoints, and you're strictly increasing or decreasing, then you're continuous. So you have, the converse is not true, but the converse plus extra assumption is true.
I like that.
Yeah, I think it's very cute. It's a lot of work. I agree. It's a jump in difficulty, but I think this is pretty...
I think I'm understanding it better now that I've described it.
Good, yeah. Okay, big picture feedback on British tutorial 2. I thought the second part, this session, was better than the first, so I was much happier. I think you understood the first, like part A and part B, like quite well, like maybe 70 to 80% of the proof I think you actually have deep in your bones. I think in the third part it was like maybe slightly less, like 60%, but you definitely understand the big picture in most of the stuff, which is good.
Yeah, I'm feeling.
Yeah, I think it's funny. I think you're well prepared for this one comparatively. The first one, I think the squeeze theorem stuff was a little shakier. I think if you were in a rush, like, I don't know, maybe you understood like half to 60% of that, but that's still fine. I mean, I just want to emphasize that it's fine to just be honest and say you don't understand shit. Like, you can just read a proof and say, yeah, I don't understand this step, but it's true that X. Like, you don't need to pretend you understand 90% of a proof if you only understand half of it to, like, impress me or something. Like, it's fine. If you understand half of it, just say the parts you don't understand. I mean, it's totally acceptable.
I'm understanding the individual steps well.
Yeah, I think that's true. Yeah, I think most of the individual pieces uh, you have pretty solidly down. But I don't know. I think when I say I understand the proof 100%, I feel like I mean like I could have produced it myself with no hints, which is like much harder than having it given to you and being able to understand the steps piece by piece. So that's fine. That's not what we're shooting for, by the way. I'm not expecting you to be able to write all these proofs with no hints from zero. That's I mean uh, that's not something you're expected to do until like you're an undergrad math major. So that's fine. I think you're
I would
doing
love to be able to do that. That's an achievement.
yeah. I mean, you take some math classes someday as part of your chemistry major, perhaps you will. But yeah, I think I'm happy with the progress. I'm ready. I'm I'm convinced that you understand limits enough to do derivatives well. But I should ask you, now that we're done with chapter 2, what are your reflections? What did you like or dislike about the limit and continuity stuff? How well do you feel you understand it, etc.?
I, I'm pretty sure I'm understanding the entire thing at 85 to 90%. Overall, I'm confident in limits now.
Okay. Yeah. All right, I'm happy with it. So, yeah, dinner tomorrow. Oh, we should do the logistics stuff. The logistics stuff I skipped at the beginning.
Yes, what is logistics?
So we should pick a deadline for Matrices Challenge 3.
Right, that thing I was due last Friday.
If it's overwhelming, we could break it up and just make the problems due on certain days, like problem 1 due tomorrow or whatever. Is that better for you, or do you just want to pick one big deadline?
Wait, what was the question again?
Would you like to break it up into smaller deadlines, like you have to finish problem 1 of Matrices Challenge 3 by tomorrow, problem 2 by Monday, and so forth? Or do you want just one big deadline, finish the whole thing by, like, Wednesday?
Hmm. I think one big deadline on Monday will.
Monday, okay.
I'm suddenly in the mood to do things.
Nice. Your bipolarness has swung the other way. Uh, good. Alright, I will write down Matrices Challenge 3 Monday, and then what should be the deadline? It's almost done. I'll just copy over.
10.5.
Well, I meant mostly the consolidation document 2 stuff. So I think 10.5 is part of it. But just copying over everything into Overleaf and fixing up all the errors and stuff. I'll give you a specific list of things to fix for what's already in there. But there's just a couple pieces that still have to be copied over and finalized. So what date should we pick for CD2 to be done?
I feel like end of week. I don't know if end of week is a bit far, but I'm comfortable with that.
So like
It's
next
just
Friday.
correct.
Okay.
What
That.
is Friday again? It's sometime in August. Oh wait. Oh my God, it's August 4th already.
Guess it'll be the 10th next Friday. Yeah, that's fine. So I'll do that either. How about this? So, in maybe by Monday or Tuesday, copy over, or even I can do it, I guess. But one of us will copy over the stuff from Piazza, the CD2 problems you've already answered on Piazza that haven't been copied over. So we'll do that. I'll write up my feedback for the things that have to be changed in the overleaf version, like the corrections, and then the deadline for implementing the corrections we could make Friday the 10th, right?
Okay.
Good. Okay. That's all my logistics. Good. I like this. I like when you're in a high mood, like on the productive mood, and lots of stuff gets done. Makes everything feel very happy and moving forward and satisfying. So, good. Other questions or stuff on your mind, calculus or not calculus related for now?
I do not have anything on my mind.
Your mind is empty. Okay, good. Then thanks for your work on the tutorial stuff, and I will see you 5 p.m. tomorrow. Right?
That is correct. Cool.
You don't sound like you're looking forward to it.
I was just looking down because I was disassembling a pen. It. Yes, I am. I am Word.
It's a thing. No, I mean, it's perfect.
What?
No, I'm just making fun of you.
I misheard something.
I'm being silly. Okay, good. I'm away.
All right.
Ciao.